All right, I want to talk about chapter 14. I'm probably going to diverge quite a bit from what's in the textbook. Mostly what I want to do is to talk about uncertainty and insurance. Um, so uncertainty is what we're talking about when we acknowledge that the outcomes that we expect from transactions aren't always the outcomes that we get. Um, So, for example, when you purchase a car, you expect you're going to drive that car until you're done with it. You don't expect that the car is going to be damaged somehow, be inoperable, and that you will need to get it repaired. And you know in your head that there's a chance that that will happen, though that's not your intent. Up to now, when we've talked about consumption, we've talked about it as though there's certainty involved in your consumption decisions. You buy the car, you get to use the car, period. Now we're going to say, suppose you buy the car, you understand that there's a 5, 10, 15, whatever it is, percent chance that the car will be damaged and that you're going to have to deal with the consequences of that. So what we want to do is to sort of set up the um, the infrastructure to understand what that looks like, consumption under uncertainty, and how that leads to the demand for insurance and insurance markets. So, to get started, what I want to do is just a little bit of a statistics um, section. We want to talk about random variables and how we work with them, because in order to talk about uncertainty, we need to think about consumption as a random variable. So that instead of getting 100 utils from purchasing an item, what I have to acknowledge is that I may get the 100 utils that I hope I'm purchasing, but it's possible that there's a 20% chance maybe that I'll get half as many utils because the thing that I'm purchasing will be damaged somehow. And how do we evaluate that? So to get started, um, first let's just talk about random variables. And I don't want to go too far down this road. I just want to make sure that we understand what it means to talk about the expected value and variance of a random variable. So suppose we have a random variable. Let's just call it x. And x takes on four potential values: 0, 10, 50, 100. Okay. And there's a probability associated with each of those values. So let's suppose that the probability that x is equal to 0 is 0.74. So 74% of the time, x is 0. And 15% of the time, it's 10. And 10% of the time, it's 50. And 1% of the time, it's 100. Okay. And so this is a probability distribution. And what I want to do is to find the expected value of x, which is going to be written as the expected value of x, and that's equal to the sum, that's uppercase sigma, which stands for sum, of x px. So what this says is find x times its probability and then sum all of those values. So x px is 0 times 0.74, which is about 0. 10 happens 15% of the time. So these are essentially, the probabilities are really weights. 74% of the weight goes to the zeros, 15% goes to the 10s. So 10 times 0.15 is 1.5. 50 times 0.1 is 5. And 100 times 0.01 is 1. And if we sum all of those, we get 7.5 is the expected value of x. Okay. So that tells us the expected value is essentially the mean of this random variable x. So this thing has a mean of 7.5. And we also want to know how dispersed are the values. Think about a situation where we have 7.5 with certainty, or these four values for an average of 7.5. On average, in each case, the variable is worth 7.5. In this case, it varies quite a bit from 0 to 100. In the case where we have 7.5 with certainty, it doesn't vary at all. And so we want to be able to distinguish between those two cases. And the way we do that is to compute the variance of the random variable. So the variance of x is going to be equal to this. We're going to take the sum of the following. We're going to take x minus the expected value of x. So for each value of x, we'll find the difference between that value and the expected value, the mean. We could just sum this, but because x is sometimes below the mean and sometimes above the mean, and the mean is right in the center, what we'll find is that if we just sum all of these up, they will offset each other, and this will always sum to 0. Okay, so if we just compute x minus the expected value of x, this doesn't sum to 0. Let's compute this. This is 0 minus 7.5, negative 7.5. 10 minus 7.5 is 2.5, and then 42.5 and 92.5. Okay. So if we take each of these and multiply them by the probability with which they occur, that difference times the probability, sum all of those up, that will sum to 0. In order to keep this thing from summing to 0 and just disappearing, what we do is we take the deviation from the mean and we square it. So we compute x minus the expected value of x squared. Okay. And so 7.5 squared is 56.25, and this will be 6.25, 1806.25, and 8556.25. Okay. So these are the squared deviations from the mean, and these will weight by the probability with which they occur. So we multiply them by the probability. So 56.25 times 0.74 is 41.625. 6.25 times 0.15 is 0.9375. 1806 times 0.1 is 180.625. And 8556.25 times 0.01 is 85.5625. We sum all that up, that sums to 308.75, and that is the variance of x. This value is a little bit difficult to interpret. Typically what we do is take the square root of it, which we call the standard deviation, and that tells us on average how much each observation varies from the mean. The variance is a little bit harder because it's in squared units. But what we can say is that if a random variable has a larger variance, then it's more variable. If we had 7.5 with probability 1, the variance would be 0. So that's no variability at all. And the more variability you have, then the bigger the variance turns out to be. We'll come back and use these concepts as we work through this material. Okay. If you've never seen this before, if you're not familiar with it, this is pretty much week 1 of a basic statistics course. And so you could find this information. Statistics textbook, or I'm sure it wouldn't be difficult to find online. Oops. All right. So let's think about consumption under uncertainty. And what I'm going to do is to use a little example to try to motivate some of the issues that underlie this. And so let's suppose that you've been unfortunate in that you need suppose you need a medical treatment, and you need a treatment, and in order to get this treatment, you need $20,000 to pay for it. Okay? If you don't get the treatment, you will die. Now the question is, how do you get this $20,000? And suppose you have two ways of getting the $20,000. And we'll refer to each of these funding mechanisms as a gamble. So gamble A, we'll describe this way. X, the number of dollars that you get, could be 10,000, could be 15,000. And the probability of each of those values is 0.5. Gamble B, the other option available to you, works this way. Call Y the payoff from this gamble. Under this gamble, you could get either $0 or $20,000. And the probabilities are 0.99 and 0.01. And so the question is, which gamble do you prefer? Well, one way we could look at this is to ask, what's the expected value of each gamble? What's the expected payoff from these two cases? So in this case, if we find X times probability of X, we can find the expected value. So half of 10,000 is 5,000. Half of 15,000 is 7,500. And that means that the expected value of gamble A is $12,500. For gamble B, we can find the expected value in the same way. 0 times 0.99 is 0. 20,000 times 0.01 is 200. And that means that the expected value of gamble B is $200. So which do you prefer? Well, one way to look at it is that on average, you get a much larger payoff with gamble A than you would with gamble B. And so maybe that makes gamble A preferred. But let's go back to your problem. The problem is you need $20,000. With gamble A, the likelihood of getting $20,000 is 0. With gamble B, the likelihood of getting $20,000 is 0.01. Which gamble do you prefer? You'd better take gamble B. Gamble B has a chance of helping you save your life. Gamble A provides no chance. Well, that's unusual, right? In the past, when we've looked at consumption issues, we've always said that the case with a larger value is the one that's going to be preferred to the lower value, right? If we're just utility maximizers, we prefer 12,500 to 200. And so what this says is that the expected utility of a gamble may be different than the expected value of the gamble. And we see that in this case because the expected value of gamble A is higher than the expected value of gamble B. But apparently the expected utility from gamble B is higher than the expected utility from gamble A, and that's why B is preferred. And so what we need to do when we think about uncertainty is to decouple utility and value. Okay, they're going to be different. And that can be meaningful in certain cases. All right, I'll take a break there. And when I come back, we're going to talk about the different kinds of consumers under uncertainty.